Hello everyone, welcome back to me learning Rust. Today we'll do the 10th chapter, I think most anticipated chapter so far. Learn about generic types, traits, and finally lifetimes. So let's just start. Every programming language has tools for effectively handling the duplication of concepts. In Rust, one such tool is generics, abstract stand-in for concrete types or other properties. And we can express the behavior of generics or how they relate to other generics without knowing what will be in their place when compiling and running the code. Functions can take parameters of some generic type instead of a concrete type like i32 or string. In the same way, a function takes a parameter with unknown values to run the same code on multiple concrete values. In fact, we've already used generics in chapter 6 with the option t, chapter 8 with the vector t and hash map with kv, and chapter 9 with result te. In this chapter, you'll explore how to define your own types, functions, and methods with generics. First, we'll review how to extract a function to reduce code duplication. We'll then use the same technique to make a generic function from two functions that differ only in the type of their parameters. We'll also explain how to use generic types in struct and enum definitions. Then you'll learn how to use traits to define behavior in a generic way. You can combine traits with generic types to construct a generic type to accept only those types that have a particular behavior, as opposed to just any type. Finally, we'll discuss lifetimes, a variety of generics that gives the compiler information about how references relate to each other. Lifetimes allow us to give a compiler enough information about borrowed values so that it can ensure references will be valid in a more situation than it could without our help. Okay. I'm suspecting this is going to be a double-parter. Generics allow us to replace specific types with a placeholder that represents multiple types to remove code duplication. Before diving into generic syntax, then let's first look at how to remove duplication in a way that doesn't involve generic types by extracting a function that replaces specific values with a placeholder that represents multiple values. Then we'll apply the same technique to extract generic functions. By looking at how to recognize duplicated code, you can extract into a function. You'll start to recognize duplicated code that can use generics. We begin with a short program listing 10.1. Okay, so let's go cargo new chapter 10. Right, let's code into chapter 10. Sorry, I'll bring this into view. Great. So now we have the main here, like this, and okay, we have function main. Let number list equals vector with 34, 50, 25, 165. Okay, I'll just copy it. No need to type it all. Let's see what we have here. We have a number list. We have a largest placeholder that has the first number in this number list, and then we loop over the number list, and if the number is greater than the largest one, we replace it. So basically, and then we print the largest number from this vector. Okay. We store a list of integer in a variable number list and place a reference to the first number in the list in a variable named largest. We then iterate through all the numbers in the list, and if the correct number is greater than the number stored in largest, replace the reference in the variable. However, if the correct number is less than equal to the largest number seen so far, the variable doesn't change, and the code moves on to the next number in the list. After considering all the numbers in the list, largest should refer to the largest number, which is in this case 100. We've now been tasked with finding the largest number in two different lists of numbers. To do so, we can choose to duplicate the code in listing 10.1 and use the same logic at two different places in a program as shown in listing 10.2. So I guess like I'm not going to copy it because it's the same code. Just here we have a different list. Yeah, that's the only difference here. We have different numbers here. Yeah, everything looks pretty much the same. So let's move on. Although this code works, duplicating code is tedious and error prone. We also have to remember update the code in multiple places when we want to change it. To eliminate this duplication, we'll create an abstraction by defining a function that operates on any list of integers passed in a parameter. This solution makes our code clearer and lets us express the concept of finding the largest number in a list abstractly. Listing tank 3, we extract the code that finds the largest number into a function named largest. Then we call the function to find the largest number in the two lists from listing 10-2. We could also use the function on any other list of i32 values we might have in the future. Let's write this function. So basically we have function largest gets a list. It's a reference to a list of i32s and returns a reference to an i32. Right? Let mutable largest equals list 0. Right? And then for item in a list, we do if item is greater than largest, we do largest equals item, and in the end, we just do the largest. Excellent. And I will copy paste this because just numbers here. And let's just run it. And we have 100 and then 6,000. Excellent. So the largest function has a parameter called list, which represents any concrete slice of i32 values we might pass into the function. As a result, we call the function. The code runs on the specific values that we pass in. In summary, here are the steps we took to change code from listing 10.2 to 10.3. We identified the duplicate code, extracted the duplicate code into a function, and update 2 instances of duplicate code to call the function instead. It's pretty basic. Next, we'll use these same steps with generics to reduce code duplication, in the same way that the function body can operate on an abstract list instead of specific values. Generic allow code to operate on abstract types. For example, say we had two functions, one that finds the largest item in a slice of i32 values and the one that finds the largest item in a slice of character values. How would we eliminate this duplication? Let's find out. We use generics to create definitions for items like function, signature, or structs, which we can then use with many different concrete data types. Let's first look at how to define functions, structs, enums, and methods using generics. Then we discuss how generics affect the code performance. Okay, so when defining a function that uses generics, we place the generics in the signature of the function, where we would usually specify the data types of the parameters and return a value. Doing so makes our code more flexible and provides more functionality to callers of our function while preventing code duplication. Continuing with our largest function, listing tank 4 shows two functions that both find the largest value in a slice. We'll then combine these into a single function that uses generics. So basically this is an example that we have like a character thing, and we have largest i32 and largest character. It's the same function, as you can see. Everything is the same. So I will not copy this. I will move to the generic part. The largest i32 function is the one we extracted in listing 10.3 that finds the largest i32 in a slice. The largest character function finds the largest characters, in a slice. The function bodies have the same code, so let's eliminate the duplication by introducing a generic type parameter in a single function. To parameterize the types in a new single function, we need to name the type parameter just as we do for the value parameters to a function. You can use any identifier as a type parameter name, but we'll use T because by convention, type parameters names in Rust are short, often just a letter. And Rust's type naming convention is upper camel case. short for type. T is the default choice for most Rust programmers. When we use a parameter in the body of the function, we have to declare the parameter name in a signature so the compiler knows what that name means. Similarly, we use a type parameter name in a function signature. We have to declare the type parameter name before we use it. To define the generic largest function, place type name declaration inside angled brackets between the name of the function and the parameter list like this. So let's copy this, and we have a largest T here. Have a T, and we do reference to T, and we return a reference to T. So I guess that's it. The compiler, like the hinter, already knows what's happened here, and the only error we have is this. And it says that it doesn't know how to compare type T. Okay. And listing type 5, we show the combined largest functions. Let's just copy this here. So we'll can run the example when this compiles. So we have a list here, and we calculate the largest, a list of i32s, and then we have a vector of character, and we calculate the largest. This seems to work, only this has an error. You can see that this cannot compile. If we compile this code right now, we'll get this error, exactly that we cannot compare this. So the help text mentions std compare partial ord, which is a trait, and we're going to talk about traits in the next section. For now, note this error states that the body of largest won't work for all possible types of T. Could be because we want to compare values of type T in the body, we can only use types whose values can be ordered. To enable comparisons, the standard library has the std compare partial ord trait that you can implement on types. See Appendix C for more on this trait. By following the help's text suggestion, we restrict the types valid of T to only those that implement the partial ord, and this example will compile because the standard library implements partial ords for both i32 and character. So let's put it here. We have std compare partial ord. And now if we save, we see everything works. And also let's run the code and see that the largest number is 100 and the largest character, yep, it's y. Excellent. Instruct definitions. And we can also define structs to use generic type parameters in one or more fields using the brackets. I don't know how to caret sign. Syntax listing 10.6 defines a point struct to hold x and y coordinates, values of any type. So yeah, and we can have like an i32 type and a float type, f32. Sorry. This syntax for using generics in struct definition is similar to that used in function definitions. First, we declare the name of the type parameter inside the angle brackets just after the name of the struct. Then we use the generic types and the struct definition where we would otherwise specify concrete data types. Note that because we used only one generic type to define point T, the definition says that the point T struct is generic over some type T, and the fields x and y are both the same type. Whenever that type may be, if we create an instance of point that has values of different types, the listing 10.7 will not work. So let's copy this. Here, see that looks okay. Then if we try to put the won't work thing, it will say an error because this is f32 and it expects an integer. Yeah, exactly, that's the error. In this example, we assign the integer value 5 to x. We let the compiler know that the generic type T will be an integer for this instance of point T. Then when we specify 4.0 for y, which we define to have the same type as x, we'll get a type mismatch error like this, and that's the error that we saw. To define a point struct where x and y are both generics but could have different types, we can use multiple generic type parameters. For example, in listing 10.8, we change the definition of point to be generic over types t and u, where x is of the type t and y is of the type u. So just with a, yeah, so if we do this and then change this to u, this will work. Great. Okay, now all the instances of point shown are allowed. You can use as many generic type parameters and definition as you want, but using more than a few makes your code hard to read. If you're finding you need lots of generic types in your code, it could indicate that your code needs restructuring into smaller pieces. Yeah. Okay. In enum definitions, as we did with the structs, we can define enums to hold generic data types in their variants. Let's take another look at option T enum that the standard library provides, which we use in chapter 6. So we have this option thing with a T, and we have some T and none here. This definition should now make more sense to you. As you can see, the option T enum is generic over type T and has two variants, some which holds one value of type T and none variant that doesn't hold any value. By using the option T enum, we can express the abstract concept of an optional value, and because option T is generic, we can use the abstraction no matter what the type of the optional value is. Enums can use multiple generic types as well. The definition of the result enum that we used in chapter 9 is one example. So yeah, here we have like OK type is T and the error type is E, and then we have, similar to this, we have two different types. The result enum is generic over two types, T and E, and has two variants, OK, which holds a value of type T, and error, which holds a value of type E. This definition makes it convenient to use the result enum wherever we have an operation that might succeed, return a value of some type T, or fail and return an error of some type E. In fact, this is what we used to open a file listing 9.3, where T was filled with a file when the file was opened successfully, and an IO error when there were problems opening the file. When you recognize situation in your code with multiple structs or enum definition that differ only in the types of the values they hold, you can avoid duplication by using generic types instead. Now we look at generics in method definitions. We can implement methods on structs and enums as we did in chapter 5, and use generic types and their definitions too. Listing 10.9 shows the point T struct we defined in listing 10.6 with a method name X implemented on it. So let's just write it, write the implementation here. So when I'm doing implementation, I'm specifying the implementation here, right? And so the type, and we have function self and T, and then self X. So let's deconstruct what's going on here. Of course, I will remove this U, put this to T, and then remove this error. This should work. So now we have a function, like we do implementation for type T for point T, and we do a function that returns a reference to the X parameter when we do like a getter or something. Just 1 second. Okay, so where were we? Yeah, so this is just like a getter. Let's play around with it and even make a getter for Y to make it complete. So now we have a function that uses the implementation with this generic here and here and here. Okay, great, let's read on. Here we define a method named X on point T that returns a reference to the data in the field X. Now that we have to declare T just after implementation, so we can use T to specify what we're implementing methods on the type point T by declaring T as a generic type after implementation. Rust can identify that the type in the angle bracket point is a generic type rather than a concrete type. we could have chosen a different name for this generic parameter than the generic parameter declared in the struct definition, but using the same name is conventional. Methods written within an implementation that declare the generic type will be defined on any instance of the type, no matter what concrete type ends up substituting for generic type. We can also specify constraint on generic types when defining methods on a type. We could, for example, implement methods only on point F32 instances rather than on point T instances with a generic type. Listing 1010 we use the concrete type F32, meaning we don't declare any types after implementation. So here, okay, so now we're implementing something specific for we have regular implementation, and we implement just for point F32, and we call it fn. Let's just shorten it for dist and do a self here with F32, and we return self x power I2 plus self y, again power of 2, and then we square everything together. Okay, so now I have a distance function that works only for F32s. This code means the type point F32 will have a distance from origin method. Other instances of point T where T is not of type F32 will not have this method defined. The method measures how far our point is from the origin and uses mathematical operations that are available only for floating point types. Generic type parameters in a struct definition aren't always the same as those you use in that same struct's method signature. Listing 1011 uses a generic types x1 and y1 for the point struct and x2 and y2 for the mix-up method signature to make the example clear. The method creates a new point instance with x value from the self point of type x1 and y value from the passed in point of y2. So we have a point with two different types, and we have an implementation for any point that uses mix-up that takes two different types and returns, okay, it takes a point of type x2 and y2 and returns a point of x1 and y2. So yeah, okay, the x from the first one and the y from the second one. So the new point is of type that we get here, and the y2 is the type that we get here. Okay, so now we have like here we have an integer, float, string, and a character, and this should return an int and a character. So let's see if we're correct. In main, we've defined point that has an i32 for x with a value 5 and f64 for y with a value 10.4. The p2 variable is a point struct that has a string slice for x with a value hello and a character for y with a value c. Calling mixup on p1 with the argument p2 gives us p3, which will have an i32 for x because x is from p1, and a p3 will have a character for y because y came from p2. The printline macro will print out that x is 5 and the y is a character c. Exactly. The purpose of this example is to demonstrate a situation in which some generic parameters are declared with implementation and some are declared with a method definition. Here the generic parameters x1 and y1 are declared after implementation because they go with a struct definition. The generic parameters x2 and y2 are declared after the function mixup because they are only relevant to the method. Okay. Performance of code using generics. You might be wondering whether there is a runtime cost when using generic type parameters. The good news is that using generic types won't make your program run any slower than it would with concrete types. Rust accomplishes this by performing monomorphization of the code using generics at compile time. Monomorphization is a process of turning generic code into a specific code by filling in the concrete types that are used when compiled. In this process, the compiler does the opposite of the steps we use to create the generic function in listing 10.5. The compiler looks at all the places where generic code is called and generates code for the concrete types and generic code is called with. Let's look at how this works by using the standard library generic option enum. So we have a sum here and a sum here. When Rust compiles this code, it performs a monomorphization. During that process, the compiler reads the value that have been used for option T instances and identifies two kinds of option. One is I32 and the other is F64. As such, it expands the generic definition of option T in two definitions specialized to I32 and F64, thereby replacing the generic definition with this specific one. The monomorphized version of the code looks similar to the following. The compiler uses different names than that we're using here for illustration. So instead of option, we have option I32, option F64. They're different, they're concise, and we can use them here. The generic option T is replaced with specified definitions created by the compiler because Rust compiles generic code into code that specifies the type in each instance. We pay no runtime cost for using generics. When the code runs, it performs just as it would if we had duplicated each definition by hand. The process of monomorphization makes Rust generic extremely efficient at runtime. So basically, the generic is like every typed language like C++. It just duplicates at compile time the code with the specific type definitions. Okay, let's go to traits. Are we on time? Great. A trait defines functionality a particular type has and can share with other types. We can use traits to define shared behavior in an abstract way. We can use trait bounds to specify a trait a generic type can be and a type that has certain behavior. Note, traits are similar to a feature often called interface in other languages, although with some differences. Okay, so we're getting into some OP things in Rust. Defining a trait, a type's behavior consists of the methods we can call on the type. Different types share the same behavior if we can call the same method on all of those types. Trait definitions are a way to group method signatures together to define a set of behaviors necessary to accomplish some purpose. For example, let's say we have a multiple struct that hold various kinds of amounts of text, a news article struct that holds a news story filled in a particular location, and a tweet that can have at most 280 characters along with metadata that indicates whether it was a new tweet, a retweet, or a reply to another tweet. We want to make a media aggregator library trait named aggregator that can display summaries of data that might be stored in a news article or a tweet instance. To do this, we need a summary from each type, and we'll request that summary by calling the summarize method on an instance. Listing 10.12 shows the definition of a public summary trait that expresses this behavior. So let's zero out our thing here, and we do a public trait summary. I guess the public here don't need it because we're not going to do a new trait, and summarize, getting a self here, self-reference, and returning a string. So basically this is like an interface that we have a function that if someone has a trait summary, it must implement this. Okay. Here we declare a trait using the trait keyword and then the trait's name, which is summary. In this case, we've also declared the trait as pub so that crates depending on this crate can make use of this trait too. As we'll see in a few examples, inside the curly brackets we declare the method signatures that describe the behavior of the types that implement this trait, which is a case of function summarize self to string. After the method signature, instead of providing an implementation with the curly brackets, we use a semicolon. Each type of implementing this trait must provide its own custom behavior for the body of this method. The compiler will enforce that any type that has the summary trait will have the method summarize defined with its signature exactly. A trait can have multiple methods in its body. The method signatures are listed one per line, and each line ends in a semicolon, implementing a trait on a type. So now that we've defined the desired signature of summary traits method, we can implement it on the types in our media aggregator. Listing 1013 shows an implementation of the summary trait on the news article struct that uses the headline. This author and the location to create the return value of summarize. For the tweet struct, we define a summarize as username followed by the entire text of the tweet, assuming the tweet content is already limited to 280 characters. So now we have a struct called the news article that has all of this. Yep. And we now implement a summary for news article. And the summary is a function summarize. Oh, it's auto-completes, and we return a formatted text that has 1 by 2 and 3, and it contains self headline, self author, and self location. Great. And now we have a tweet here, and for tweet we implement summary for tweet, and we have a function summarize that returns a format of like this, and we have a self username and a self content, right? Excellent. So now we've implemented everything here. Okay, implementing a trait on a type is similar to implementing irregular methods. The difference is that after implementation, we put a trait name we want to implement, then use for keyword, and then specify the name of the type we want to implement the trait for. Within the implementation block, we put the method signature that the trait definition has defined. Instead of adding a semicolon after each signature, we use a curly brackets and fill the method body with specific behavior that we want the method of the trait to have for the particular type. Note that the library has implemented the summary trait on news article and tweet. Users of the crate can tell the trait method to an instance of new article and tweet in the same way we call regular method. The only difference is that the user must bring the trait into scope as well as the type. Here's an example of how a binary crate could use an aggregator library crate. So we have a method here. So we created a tweet, and then we print a summary of the tweet. Let's do this. Let's run. We have a warning. Never mind. One new tweet. And we have a summary, which, of course, ebooks. Of course, you probably... Okay. Great. Okay, the code prints this. Yep, it printed. Other crates that depend on aggregator crate can also bring summary trait into scope to implement summary on their own types. One restriction to note is that we can implement a trait on a type only if at least one of the trait or types is local to our crate. For example, we can implement standard library traits like display on a custom type like tweet as a part of our aggregator crate functionality because the type tweet is local to our aggregator crate. We can also implement summary on vec in our aggregator crate because the trait summary is local to our aggregator crate. But we can't implement external traits on external types. For example, we can't implement the display trait on vec t within our aggregator crate because display and vec t are both defined in a standard library and aren't local to our aggregator. This is really good, actually. It prevents a lot of unknown behavior that some crate can influence your code with. This restriction is a part of a property called coherence, and more specifically, the orphan rule. So named because the parent type is not present. The rule ensures that other people's code can break your code and vice versa. Without the rule, two crates could implement the same trait for the same type, and Rust wouldn't know which implementation to use. Okay. Default implementation. Sometimes it's useful to have default behavior for some or all of the methods in a trait instead of requiring implementation for all methods on every type. Then we use, as we implement the trait on a particular type, we can keep or override each method's default behavior. In listing 1014, we specify default string for the summarize method of the summary trait instead of only defining a method signature. So basically we just, instead of a semicolon here, we just do a string from and read more. Read more, yep, like this. And now if we don't want to do this, yeah, news article, it will still work. So let's copy this and I'll read up to it. Don't worry, just want to see that it works. It doesn't work. Let's see why. Okay, so listing 410 specified default string for the summarize method. Let's see that we wrote this correctly. So we have a string here from read more. Everything looks okay. To use default implementation to summarize the instance of news article, we specify an empty implementation block with implement summary for news article. Okay, so we do, need to implement, we need to implement summary for news article, and then an empty block, right? Yeah, and then an empty block, and then the error disappears. This tells that to attach this implementation to the news article. Okay, excellent. Even though we're no longer defining summarize method on a news article directly, we've provided a default implementation and specified that news article implements the summary trait. As a result, we can still call summarize method for an instance news article like this. Let's just run it and get news article available, read more. Okay, great. This code prints this. Creating a default implementation doesn't require us to change anything about the implementation of summary on tweet using in listing 1013. The reason is that the syntax of overriding a default implementation is the same as the syntax for implementing a trait method that doesn't have a default implementation. Default implementation can call other methods in the same trait, even if those other methods don't have default implementation. In this way, a trait can provide a lot of useful functionality and only require implementers to specify a small part of it. For example, we could define the summary trait to have summarize author method whose implementation is required, and then define a summarize method that has default implementation that calls the summarize author. So now we're adding summarize author function to the trait like this, and now we implement summarize author for a tweet. Right, and also, wait, let's, here, read more from, right? Read more from this, and then we put here the self summarize author. Like this. So now it's format, not string from. Yep. Okay. So we have a tweet, and here we do need to implement this. So let's implement a summarize author, and it will just be self author. What's the error here? Cannot move out of self, which is behind. Okay, so we copy like this. No. Doesn't implement the copy. So we'll do here string from this. Will this work? Still no. Do I have anything as character? Let's see, characters here. Characters, and then from characters. We have something from characters? No. Okay. Oh, still doesn't work. I wonder why. Maybe there's a clone thing here. Clone. Okay, this should work. Great. So we've solved this. So now this should work. Let's run it. New article. Read more from Iceberg. Okay, great. After we define the summarize author, we can summarize on instances of tweet struct, and the default implementation of summarize will call the definition of summarize author that we've provided. Because we've implemented summarize author, the summary trait has given us the behavior of the summarize method without requiring us to write any more code. Okay, so now we have this tweet, and we can run this code as well. And this should, also work. One new tweet, horse ebooks. Okay. Great. This code prints this. Oh yeah, we need to remove the summarize from the tweet to make it same. So yeah, good. Okay, traits as parameters. Now that you know how to define, note that it isn't possible to call the default implementation from an overriding implementation of the same method. Okay, this is good. That means that it is static. Like once I've overridden something, it's static within the file. Like I cannot choose it. There's not dynamic way to say, okay, I want to run the previous function before overriding the overridden function. Okay. Traits as parameters. Now that you know how to define and implement traits, we can explore how to use traits to define functions that accept many different types. We'll use the summary trait we've implemented on the news article and tweet types in listing 1013 to define a notify function that calls the summarize method on its item parameters. So now we have to define a new function. Okay, so now we have a function that has called notify. It gets an item, which is a reference to an implementation of summary. And then we just print line breaking news. And then we take the item and we summarize it. And semicolon, because you don't want to return anything. Instead of a concrete type for the item parameter, we specify the implementation keyword and the trait name. This parameter accepts any type that implements the specified trait in the body of notify. We can call any method on item that comes from summary traits, such as summarize. We can call notify and pass in any instance of news article or tweet. Code that calls the function with any other type, such as string or I32, won't compile because those types don't implement summary. This is interesting. I wonder how if it compiles two versions of notify just for this or not. Well, we'll see. The implement trait syntax works for straightforward cases, but it's actually syntax sugar for a longer form known as a trait bound. It looks like this. Okay, so this is the answer. It does create two functions because it's like generics. So here we have notify T, and T is a type of summary, and then we do this. Okay. This longer form is equivalent to the example in the previous section, but is more verbose. We place trait bounds with a declaration of the generic types parameter after a colon and inside angle brackets. The implement trait syntax is convenient and makes for more concise code in simple cases, while the fuller trait bound syntax can express more complexity in other cases. For example, we can have two parameters that implement summary. Doing so with the implementation trait syntax look like this. Using the implementation trait is appropriate if you want this function to allow item 1 and item 2 to have different types, as long as both types implement summary. If you want to force both parameters to have the same type, however, we must use a trait bound like this. So now we have a trait, which is a summary, and items 1 and 2 have to be the same. Okay, the generic type T specified as the type of the item 1 and item 2 parameters constrains the functions such that the concrete type of the value passed as an argument for item 2 and item 1 must be the same. Specifying multiple trait bounds with the plus sign syntax. We can also specify more than one trait bound. Say we want to notify to use the display formatting as well as summarize on item. We specify the notify definition that items must implement both display and summary. We can do so using the plus syntax. Okay, so and we have brackets here. Okay, and the plus syntax is also valid with the trait bounds on generic types. Okay, with the two trait bounds specified, the body of notify can summarize and use the curly brackets to format item. Okay, using too many trait bounds has its downsides. Each generic has its own trait bounds, so functions with multiple generic types parameters can contain lots of trait bound information between the function's name and its parameter list, making the function signature hard to read. For this reason, Rust has alternative syntax for specifying trait bounds inside a where clause after the function signature. So instead of writing this, well, we have like a T, which is a display and a clone, and a U, which is a clone and debug. We can use this some function like this, where T is display clone. Okay, so it's just easier to read this. Okay, this function's signature is less cluttered. The function name, parameter list, and return types are close together, similar to function without lots of trait bounds. So basically, it just shortens the function signature and makes it more readable. Okay, returning types that implement traits. We can also use the implementation trait syntax in the return position to return a value of some type that implements a trait, is shown here. Okay, so we have like returns implement. Okay, these. Okay, so we're just creating. We say I'm saying I'm returning something that implements a summary. Okay, and then I'm returning a tweet. Okay, by using implement summary for the return type, we specify that the returns summarizable function returns some type that implements the summary trait without naming the concrete type. In this case, returns returns summarizable, returns a tweet, but the code calling this function doesn't need to know that. The ability to specify the ability to specify a return type only by the trait it implements is especially useful in the context of closures and iterators, which we'll cover in chapter 13. Closures and iterators create types that only the compiler knows, or types that are very long to specify. The implement trait syntax let you concisely specify that the function returns some type that implements the iterator trait without needing to write out a very long type. However, you can use the implement trait if you're returning a single type. For example, this code that returns either a news article or a tweet with the return type specified as implement summary wouldn't work. Okay, let's look at the error that we have. What it says: if and else have incompatible types. Sorry. Returning either a news article or a tweet isn't allowed due to restrictions around how the implementation trait syntax implemented in the compiler. We'll cover how to write function with this behavior in the using trait object that allow for values of different types in chapter 17. And we undo this. Okay. Using trait bounds to conditionally implement methods. By using a trait bound with an implementation block that uses generic type parameters, we can implement method conditionally for types that implement the specific trait. For example, the type pair in listing 1015 always implements the new function to return a new instance of pair. Now, recall from the defining method section of chapter 5 that self is a type alias for the type of the implement block, which is in this case is pair t. But in the next implementation block, pair t only implements the compare display method. If its inner type t implements the partial OR trait that enables comparison and the display trait that enables printing. Okay, so now we have the structure which have x and y. It's a pair, and we have an implementation of a new that just creates a new function, like a new pair, and we have implementation of t that has a display and partial ORed of pair. Yeah, so we implement only for types which has display and partial ORed, and then we can compare the display, which compares x and y, and then prints it out. We can also conditionally implement a trait for any type that implements another trait. Implementations of a trait on any type that satisfies that trait bounds are called blanket implementation and are extensively used in Rust standard library. For example, the standard library implements the toString trait on any type that implements the display trait. The implement block in the standard library looks similar to this. So we have like every type which has a display will have now implementation of a toString. Wait, there's a 4t. Implement toString, 4t. For any type that has a display, we implement this trait, which is toString. Okay, because the standard library has a blanket implementation, we can call the toString method defined by the toString trait on any type that implements the display trait. For example, we can turn integers into their corresponding string values like this because integers implement display. Blanket implementation appear in the documentation for the trait in the implementers section. Traits and trait bounds let us write code that uses generic type parameters to reduce duplication, but also specify to the compiler that we want the generic type to have a particular behavior. The compiler can then use the trait bound information to check that all the concrete types used with our code provide the correct behavior. In dynamically typed languages, we would get an error at runtime if we call the method on a type which didn't define the method, but Rust moves these errors to compile time, so we're forced to fix the problems before our code is even able to run. Additionally, we don't have to write code that checks for behavior at runtime because we've already checked at compile time. Doing so improves performance without having to give up the flexibility of generics. This is actually really good. This is like very similar to generics in C++, but removing a lot of the object orientation and inheritance that you see in C++ and sticking to very specific rules of implementation actually makes it easier to do all the checks in compile time and not depend on some virtual tables at runtime. So yeah, let's see what's next. Lifetimes. And it looks like a long chapter. I think we'll leave it for next time. Thank you very much. See you.